Hi, this is the third video in the kinematics section, and this is about graphs. We're particularly applying it to Suvat equations. That means constant acceleration, although the use of graphs is also appropriate if acceleration is non-zero. We're not going to cover that. I think once we've covered this, it starts to become a bit more obvious later on, once we've done non-constant acceleration. So what are we talking about? Essentially, most of the graphs that you'll see in A-level examination questions, at least, will be velocity time graphs. We're not limited to those. We may see displacement time graphs and acceleration time graphs. But again, I think if we cover velocity time graphs, it really it kind of leads you on to what we need to do in the case of displacement and acceleration. So we're just dealing here with velocity time graphs. So here's this graphic kind of summarizes things quite nicely. Here's an example of a velocity time graph. It's actually in 4 sections here, and these are all straight lines, and the reason they're straight lines is because we are talking about constant acceleration. So if acceleration is constant, that means the rate of change of velocity with time is constant. And if the rate of change of velocity with time is constant, then we're going to expect these to be straight lines. And the straight line might be a horizontal line if the rate of change is 0, and it will be negative if the rate of change is decreasing. So that's deceleration. So this is some object, some particle, actually over a period of 10 seconds. It starts off by accelerating, then it goes for a couple of seconds at constant velocity of 3 meters per second in actual fact, and then it accelerates again up to 6, and then it immediately decelerates down to 0. So we've got constant speed here, the blue, deceleration. Now the gradient of this line actually tells you, if we can measure that, it actually gives us the acceleration, and we can measure it because we look at the rise over the run. Here, let's just look at this red part here. We've got rise over run. Well, the rise is 3, the run is 4. So the rise over the run would be 3/4, or 0.75, and that would be an acceleration of 0.75 meters per second. So that would correspond to that, and so on. And we can do that here, even this is negative, so it's going to give us a negative number. The other interesting thing and useful thing about velocity time graphs is if we take the distance underneath this line, then we get the distance traveled. Assuming this is all above, we've got constant positive, not constant, but positive velocity here, then the distance is the same as the displacement, so we use the term distance here. And it's actually equal to the area. Well, that's not too surprising, is it? Because distance equals velocity times time. That's going back to one of our Suvat equations. And if we just look at this section here under the light blue line, so distance equals velocity times time. Well, the height is the velocity, the base is the time. So if we multiply the base times the height, we're multiplying velocity times time, and therefore the area is the displacement, or distance in this case. And then we've got the same thing here. We're dealing with triangles, so half base times height in those situations. So that is a velocity time graph. And the point here, which you may have already triggered, is that actually this is going to be quite useful in solving problems, because we we can start to use the area and the slope in order to be kind of supporting the Suvat equations. So we'll see that when we do some examples in a moment. The only other thing I think, as I've already alluded to, is that velocity time graphs are still relevant, even if the acceleration is not constant. If the acceleration is not constant, then we may have curves here, curved lines, which you know, is the essential difference. So so we'll come back to that in a future video. Okay, so let's have a look at an example. And here is one. Now, it's a bit of a long example. This, in fact, I can't even fit it on one page of the screen. But let's just have a go and see where we get. Okay, so this is a velocity time graph of something. This one is in 3 phases: an acceleration, constant velocity, and then a deceleration. I've split these into phase 1, 2, and 3. And accordingly, we'll say just a bit of notation that the time associated with each phase is ti time phase I. So T1 will be the time for phase 1, T2 for phase 2, and so on. And then correspondingly, the displacement or distance, SI, so S2 would be the distance traveled in this phase 2. Okay, now, so I've created my notation here, which is, I think, what I previously said you may need to do, really just you know, it's to make it easy for yourself, really. I don't want to confuse between T1 and T3 or S2 and S1 or whatever. So that's useful in this particular problem. There's only one particle here, so I haven't kind of distinguished. No need to distinguish between the time for one particle and the other. So yeah, so it's just appropriate for what we're doing in this question. Let's just read through the question, see where we're going to. The velocity time graph in figure 4 represents the journey of a train P traveling along a straight horizontal track between 2 stations 1.5 kilometers apart. And one thing to note here is, of course, we deal in meters when we do these problems, so we need to do a bit of a conversion here. So that is actually 1500 meters, so we need to just remember that. Train P leaves the first station accelerating uniformly for rest for 300 meters. That's this bit going up here, until it reaches a speed of 30 meters per second. The train then maintains this speed for t seconds, it's marked on here, before decelerating uniformly at 1.25 meters per second, coming to rest at the next station. So we're given, well, we're given that this velocity is 30 here. We're given what this distance is, which of course is the area here. And we're given the slope of this line. So we're kind of given a mixture of things, something missing, if you like, for each phase. And of course, we're probably going to expect that in order to actually answer the question, we need to sort of fill in the bits of information that we haven't been given. So here we go. Part A, find the acceleration of P during the first 300 meters of its journey. And there we go. That is straight off. That's what we need to do. So, so the acceleration is going to be the rise over the run. We know the rise. We don't know the run, but we can find out the run because we've got the area of this. And of course, this area, the distance, is going to be a half base times height. So we can put that into a little equation. Half base times height equals the distance stroke displacement, 300. So we've got a little equation in T1 there, the time for the first phase. So that simply gives us that T1 equals 20 seconds. So that's what that bit is there, 20 seconds. Right, so now we've got the rise and the run, so we can actually work that out. So we'll use this Suvat equation, A equals V minus U over 2, TV being the final velocity and U being the initial velocity. Well, that one, the initial velocity is 0, isn't it? V is 30, so 30 minus 0 over 20, time period 20. and that's giving us 1.5 meters per second. So that is what that the acceleration is over that period, which is the gradient of the line. Okay, so that's good. Let's look at part B, the value of t. Okay, so we need to know what this is. Okay, so just have a look at that. Okay, so first of all, what we need to do here, let's just try and unpick what we need. We know that time. We know that distance. If we knew this distance, then we know that the total distance is 1500. So if we could work out this distance, take this and this away from 1500, we would get this distance. And then, so we know this area, and the area is equal to the base times the height. So that's going to give us that period there. So that sounds like a plan. So let's have a look. What do we need to do in order to find this? Well, let's have a look at this. For this phase 3, we know the acceleration, that's given in the question. We know the initial velocity, that's u. We know the final velocity, it comes to rest here. But we don't know the distance or displacement. So what have we got? We've got v, u, a, s. It looks tailor-made for v squared equals u squared plus 2as, one of our armory of Suvat equations. Okay, so let's just plug those things into there. And well, we'll not go through the working, but you know, the only thing we don't know in there is s. That's 3, of course. So if we just work that through, we're going to get s3 equals 360. Okay, right, I'm going to skip this bit. Perhaps I should have put this in the bit further down. We don't need that just yet. But let's have a look at this. So S2. So this distance here is going to be this 1500 minus this distance minus this distance. Well, we've given that 300. We've worked that out. That's 360. So that gives us a total distance in phase 2 of 840 meters. So there we go. So S equals VT. S equals VT. Well, V is this constant velocity, and T is the time. So again, so just work that through, and that's T equals 28 seconds. So this period here is 28 seconds. So things are going quite well here. We've got this time, we've got this distance, we've got this acceleration, we've got this time, we've got this distance, 840. We've got the velocity there, but of course it's the acceleration is 0. And on this bit, we've got the acceleration, deceleration as it is, and we've got the distance as well, which we worked out to 360. So we know quite a bit. So that's all quite good. So really, we've trained P, we've answered the questions, but goes on, a second train Q completes the same journey in the same total time. The train leaves the first station accelerating uniformly from rest until it reaches a speed of V, big V meters per second, and then immediately decelerates uniformly. Uniformly means constant deceleration. Comes to rest at the next station. Sketch a velocity time graph for Q. Okay, well, it's just told us it's the same time. So the length of this kind of bit is going to be the same. This one just accelerates and decelerates though. So there's no kind of plateau on the top of this one. Goes up and then down. So we just got a triangle representing this journey. And it goes on to say, find the value of V. So this is the velocity time graph. So we've done part A, part C, And then D is find the value of V. Okay, so now in order to do this, well, again, we know it's 1500, same journey. And this area here is going to be half base times the height. Okay, and the total time, it's done in the total time, so that is this T1 plus T2 plus T3. Well, we actually know T1 and T2 from the first two bits of the question. We worked out T1 is 20, T2, which is this same as this big T, 28 seconds. We don't actually know T3. So this is where we're just nip back up here into this bit, and we can apply to phase 3. We can apply this Suvat equation. The final velocity, which is 0, is equal to the initial velocity, which is 30, times the acceleration, which we know to be minus 1.25, and that will give us the time. So we can work out the time for phase 3 from that, and that's 12 seconds. So quite simply, we can just put this all together and work this out. So total time is this 60 seconds. That's 20 plus 28 plus 12, that's 60 altogether. And if we just work that through for big V, then we find that V is equal to 50 meters per second. So that is how we've done that. So quite a nice problem. One or two things we have to notice. I mean, it's not totally straightforward, but you know, we're basically, as you can see, we're using the geometry of the situation in order to help us apply the Suvat equations. You could do it without the graph. You could do it, but it's a lot easier when you can see it and you can actually kind of relate particularly the distance, I think, with the area. Okay, so so that's that question. Now let's have a look at this one, and then I think we've got two good examples under your belt. Okay, so this black line here is going to be the velocity time graph. A car is moving along a straight road. Time t, the car is moving with speed 20. You can see that going on there. And is at the point A there. It maintains the speed of 20 for 25 seconds. That's that 25 seconds there. Along there. And then it moves with constant deceleration of 0.4 meters per second. That's what it's doing there. Reducing its speed from 20 to 8. It's the 8. And then it moves along at 60 seconds at that velocity of 8 meters per second. And then it moves with constant acceleration, straight line, until it's moving with a speed of 20 meters per second at the point B. The red bits we don't really know at this stage. I've just marked those in because that's part of the solution. But when we start off, we don't know these. So first part is sketch a speed time graph. Well, we've done that. The grey lines, incidentally, I've just put in to help divide this up into portions because we're going to need to do that in a moment. And find the time for which the car is decelerating. Well, the only time it's decelerating is when it's coming down from 20 to 8. So let's have a look at this. So the acceleration is deceleration in actual fact. Again, we need to be clear about our signs. Motion we don't know which direction it is, but in the forward direction, let's say, is is positive, but it's decelerating, so that deceleration is negative. So here we go. So just apply this Suvat equation. The acceleration is equal to the difference in velocity divided by the time. That's meters per second. Think of it like that. If you forget the equation, you can easily sort of put it together. That's going to be equal to old minus 20 over T2. I'm supposed to be 8, I think there. Over T2 equals minus 0.4, and that's going to give us 20 seconds for this period here. Okay, so we've done part B. Given that the distance from A to B is 1,960 meters, so in other words, the total area under here, 1,960, find the time taken for the car to move from A to B. Right, well, what we want is this whole thing, this length here on the graph. And now we know this, we've calculated that, we know that, given the ones in black. We don't actually know this. So how do we calculate that? Well, in order to do that, we kind of need we can calculate that if we know what this area is. Because we know this distance and we know this distance. This is a trapezium here. So if we know both of these lengths here, then and we know the width, we'll be able to equate it to the area. So let's have a look at that. So the total distance for this phase is going to be given by this equation. Well, the total distance for the whole thing is 1,964, and that's made up of this area, which is going to be 25 times 20. Like that. It's going to be this area, which I've split into two. Could do as a trapezium, but I've chosen to do it as a rectangle and a triangle. So this lower bit is 20 times 8, base of 20 times 8, and the upper bit's half base times height, and so that's half times 20 times 20 minus 8, 20 minus 8. It's 12, the height is 12, isn't it? So it's half times 12. 20 times 12, what's that? And then this area, which is simply 60 times 8, base of 60, height of 8, plus S4, plus what we've got here. So there we got an equation in S4. We just need to work that through, and that will give us S4 is 700. So this area here of this trapezium is 700. But that trapezium is, well, it's that times T4 times 8, base times height. And then it's half base, so it's half of the base, times this height for the triangular bit. So half times T4 times 20 minus 8. Okay, so we just simplify that. It gives us 14 times T4. And that is equal to 700. And quite simply, therefore, the time for the fourth bit is 50 seconds. This is 50 seconds. I've written it in red. And all we need to do is add up these 4 bits. And that gives us 155 seconds. So that is the time taken for the car to move from A to B. Okay, so, you know, these things are a little bit of a jigsaw puzzle, I suppose. You know, we're using some bits of information to find other bits of information. It's all about acceleration, velocity, displacement, and time, applying our Suvat equations. And we've got a diagram. It just makes our thinking processes a little bit clearer, but we're not actually applying anything really new. It's just a graphical way of applying the Suvat equations. In fact, so it's just an aid. So there we go. So that is that question. So I hope you find that useful and interesting. And we've got some more yet to do in the kinematics section, and I'll see you in the next video.